In 2025, the interstellar object 3I Atlas swept into our solar system. A visitor formed around another star. Thermal models and heat maps were expected to confirm familiar volatile patterns. Instead, beneath its dark surface, the data revealed a thermal puzzle no known object has shared. Why does 3I Atlas break the rules, and what can its heat reveal about its origins? Thermal modeling of the interstellar object. 3I Atlas begins deep in interstellar space, long before sunlight has any effect. The simulation grid is initialized 6,500 days before perihelion, when the object is more than 100 astronomical units from the Sun. At this distance, solar heating is negligible, so the entire surface and subsurface are nearly the same temperature, set by the faint background of starlight. This creates a stable, near isothermal starting point. The model grid extends downward from the surface in fine layers, each just 5 millimeters thick, reaching a total depth of 10 meters. Time zero on the heat map corresponds to this moment, with every layer at equilibrium. From here, the simulation will track how heat slowly penetrates downward as 3I Atlas moves closer to the Sun. The axes of the heat map, depth and time, are now defined, setting the stage for exploring how each parameter will shape the evolving thermal story. Key thermal properties shape every contour on the heat map. The sublimation thresholds for the main volatiles are sharply defined. Carbon monoxide becomes active around 30 Kelvin, carbon dioxide around 80 Kelvin, and water ice only above 150 Kelvin. These temperature boundaries act as invisible lines that move through the subsurface as 3I Atlas approaches the Sun. The model assigns a bulk density of 1,000 kilograms per cubic meter, typical for porous, volatile-rich bodies. Specific heat capacity is 550 joules per kilogram per Kelvin, capturing the energy required to raise the material temperature. Surface emissivity is 0.95, so almost all absorbed energy is re-radiated as heat. Albedo, the fraction of sunlight reflected, is capped below 0.2. This dark surface ensures enough energy is absorbed to reach the critical temperatures for water ice activity. Together, these parameters control how and where heat travels, defining the subsurface boundaries that will reveal unusual behavior beneath the surface. As 3I Atlas draws closer to the Sun, the heat map reveals a striking pattern. Water ice requires temperatures above 150 Kelvin to sublimate, and it only becomes active in the very top layers of the surface. Even at perihelion in late October 2025, the thermal model shows that this activation is limited to the upper 15 to 20 centimeters. Beneath this shallow zone, temperatures remain well below the threshold needed for water ice to turn into vapor. The deeper subsurface stays cold and undisturbed, preserving its original state despite the rising solar energy at the surface. This behavior contrasts with what might be expected from a volatile-rich object exposed to intense sunlight. The heat simply cannot penetrate far enough, even when the surface is at its warmest. This shallow water ice activation is a clear marker on the heat map, and it prepares us for a deeper look at how other volatiles behave within 3I Atlas. Carbon monoxide and carbon dioxide become the main drivers of activity as the interstellar object 3I Atlas approaches the inner solar system. Unlike water ice, these carbon-bearing volatiles begin to sublimate at much lower temperatures, with carbon monoxide near 30 Kelvin and carbon dioxide around 80 Kelvin. Thermal models show that their sublimation fronts are not confined to the uppermost surface. Instead, these boundaries can extend meters below, especially during the months after the object crosses the solar system ice line. Observational data from SphereX in December 2025 captured this regime shift firsthand. Roughly 3.5 months after perihelion, the heat map reveals a deepening of the volatile fronts, with carbon monoxide and carbon dioxide activity dominating at substantial depths, while water ice remains stable below the top layers. This pattern is unusual. Deep-seated carbon volatiles remain active long after the shallow water ice zone has stabilized. The contrast between shallow and deep volatile activity stands out sharply, setting up a puzzle about how heat and composition interact in the interior of the interstellar object, 3I Atlas. Heat travels slowly through the surface of the interstellar object, 3I Atlas. Even when the Sun is at its brightest, only the uppermost layers show any real temperature change. Thermal models use conductivities typical of porous, organic-rich materials, for example between 0.1 and 0.5 watts per meter per Kelvin. This low conductivity means heat struggles to reach beneath the first few centimeters, leaving the interior cold and unchanged. The surface must be exceptionally dark, with an albedo below 0.2, for enough sunlight to be absorbed and trigger water ice activity at all. The result is a world where the exterior responds to solar energy, but the deeper layers remain locked in their original ancient cold. Independent thermal models converge on the same unusual pattern. The interstellar object 3I Atlas combines deep-seated carbon volatiles with water ice activity that is restricted to a thin surface layer. Compared side by side with typical solar system objects, this split between shallow and deep volatile activation stands out. The agreement among models highlights a thermal profile that preserves evidence of its interstellar journey. Every layer of 3I Atlas holds a thermal record from another star. As silent fragments drift between worlds, we're reminded that the universe's secrets rarely match our expectations. Thanks for watching.